Imagine you are sitting by a fireplace in a completely dark room, with only the flickering light of the flames illuminating the old walls covered in layers of dust from countless stars. The crackling sound of burning wood blends with the howling wind outside the window, as if the universe itself is whispering ancient secrets. Today, we will embark together on a long and captivating story, where gigantic monsters lurk in the shadows of space, beings that carry pitch-black hearts capable of swallowing both light and hope. These are not living creatures, yet they are so powerful that entire galaxies tremble in their presence. They are black holes, the most vivid proof of the destructive power of the universe, sources of nearly infinite energy that are ferocious and mysterious to the extent that millions of scientific articles written in every language on Earth have still not fully unraveled their secrets. For humanity, black holes remain the darkest and most enigmatic objects, like ghosts haunting the dreams of astronomers. Picture yourself scrolling through your phone screen late at night when everyone else is fast asleep, and suddenly the search term black hole appears at the top of trending topics about the universe. It is always there, defying the passage of time, because humans have never stopped being curious about the immense power of these enormous black spheres. We have never encountered them directly, but just thinking about something surviving a confrontation with them sends a chill spreading from the depths of your heart. Nothing can defeat them, at least not yet. Black holes always emerge victorious, like undefeated kings in a kingdom of darkness. On this journey, we will delve deeper together into the magnificent giant black holes, the destroyers with hearts of darkness, through the relentless efforts of generations of scientists across the planet. Every time a massive star fades away, a brilliant supernova explosion lights up the cosmos like a final fireworks display, and from the ashes of that event, a black hole is born. Imagine the scene: a star hundreds of times heavier than our Sun, after billions of years of shining brightly, suddenly collapses in an instant, creating a region of space where time itself is warped and light is completely devoured. In our familiar Milky Way galaxy, home to hundreds of billions of stars dancing like fireflies in the night, at least 100 million black holes with masses equivalent to stars are hiding. Among the stars that are still shining brightly, for every 1,000 stars, one is massive enough to collapse into a black hole when its fuel runs out. Now, expand your view to the observable universe, where light from distant galaxies takes billions of years to reach us. Based on incomplete statistics from telescopes such as Hubble and James Webb, scientists estimate there are about 2 trillion galaxies. So if you ask how many black holes exist in the universe, the answer is similar to asking how many grains of sand are in the Sahara Desert. They are so numerous that counting them becomes meaningless, like trying to embrace the entire ocean with bare hands. The mass of a black hole ranges from a few 100,000 tons to the weight of a small galaxy, and they are classified into 4 main types: micro-black holes, stellar mass black holes, intermediate mass black holes, and supermassive black holes. Let us start with the smallest ones, micro-black holes, also known as primordial black holes. This is a fascinating hypothesis that has not yet been proven in reality, proposed by physicists like Stephen Hawking in the 1970s. They are only the size of an atom or even smaller, weighing from a few 100,000 to a few billion tons, and their lifespan is extremely short, lasting only seconds. To date, although missions like LIGO and Virgo have detected gravitational waves from dozens of black hole mergers, no micro-black hole has been directly observed. However, they are believed to play a crucial role in quantum effects immediately following the Big Bang, about 13.8 billion years ago. Imagine this: if a primordial black hole were to pass through Earth, it would cause a shock equivalent to a magnitude 4 earthquake on the Richter scale, shaking everything from the foundations of buildings to the planet's core, even though its size is so tiny that it cannot be seen with the naked eye. Next come the stellar mass black holes, the most common and best understood type. They weigh from 3 times to several hundred times the mass of the Sun and form from the gravitational collapse of massive stars through supernova events. Picture a star like Betelgeuse in the Orion constellation, 20 times more massive than the Sun. When it exhausts its hydrogen and helium fuel, its core collapses in a fraction of a second, forming a black hole. This is the type of black hole that scientists like Kip Thorne, who contributed to capturing the first image of a black hole in 2019 by the Event Horizon Telescope, understand best through mathematical models and indirect observations. Larger still are the intermediate mass black holes, with masses around 1,000 times that of the Sun, up to less than 1 million times. According to theory, no single star is heavy enough to form them naturally, and to date, no direct observations have confirmed their existence, although some potential candidates are being monitored at the centers of large star clusters or dwarf galaxies. Telescopes like NASA's Chandra X-ray Observatory frequently scan these regions, hoping to capture X-ray signals from matter being pulled in. Finally, the kings of darkness, supermassive black holes, weighing millions to billions of times the mass of the Sun, with no upper limit preventing their growth. As of now, TON 618, abbreviated as TON 618, remains the largest discovered black hole, equivalent to 66 billion times the mass of the Sun, located at the center of a distant quasar. But this list is changing rapidly. New discoveries from the James Webb Space Telescope in 2023 and 2024 reveal some black holes exceeding 100 billion times the Sun's mass, puzzling scientists because they existed just a few 100 million years after the Big Bang. All supermassive black holes reside at the centers of galaxies, including Sagittarius A star at the core of our Milky Way, weighing about 4 million times the Sun. This implies at least 2 trillion supermassive black holes in the observable universe. But the greatest mystery is how they form. Observations from the Hubble Space Telescope show some supermassive black holes existed when the universe was only 800 million years old, while the time for the first stars to form was 380 million years after the Big Bang, too short for them to grow from ordinary stellar collapse. A typical star is only a few hundred times the Sun's mass, and during a supernova, it ejects 70 to 75% of its mass, leaving a core of just a few percent of the original. Even the hypothesis of dark stars, powered by dark matter for superior energy, remains theoretical, as no such massive stars are found today. Most observed supermassive black holes are quasars, shining brightly due to accreting enormous amounts of matter. However, they accrete matter more slowly as they grow, due to the Eddington limit. Radiation pressure pushes matter away when friction heats the accretion disk to millions of degrees. Black holes convert 10% of accreted mass into energy, far more efficient than nuclear fusion in stars, which achieves only 0.5 to 0.7%. Quasars are the most extreme phenomena in the universe, with X-rays and gamma rays erupting like cosmic storms. To grow rapidly in a few 100 million years requires a more powerful mechanism, mergers. By 2025, the LIGO-Virgo-Kagra collaboration had detected over 90 black hole mergers, mostly stellar mass, releasing energy equivalent to billions of stars. Estimates suggest hundreds of millions of such mergers are needed to create one supermassive black hole, and with 2 trillion supermassive black holes, the total number of mergers reaches an astronomical figure. Each merger produces gravitational waves that ripple through space, vibrating like whispers from the early universe. Ultimately, black holes might accrete dark matter or combine all mechanisms. Their existence is undeniable, but their origins remain legendary. Like wind brushing the cloaks of giants, science only lightly touches the secrets. Now, let us shift to another aspect: density, the terrifying compactness of the universe's heaviest substances. Imagine holding a teaspoon of material from a neutron star's core. It would weigh as much as a mountain. That is reality. To measure density, we calculate mass per unit volume, in kilograms per cubic meter. Starting with the sparsest, the vacuum of space. According to quantum mechanics, vacuum is not completely empty. It contains lone hydrogen atoms and dark energy, but stripping everything away, the density is 10 to the power of minus 27 kilograms per cubic meter, so light you would not feel it. Next, hydrogen gas, the lightest in the universe, 81 million trillion times denser than vacuum under standard conditions, 0.09 kilograms per cubic meter. To hold 1 kilogram, you would need a container 11 cubic meters in size. Then aerographite, a carbon foam from Zhejiang University in China, with a density of 0.16 kilograms per cubic meter, 7.5 times lighter than air. Familiar air, 1.2 kilograms per cubic meter. Each day, you breathe in 13.2 kilograms. Water, 1,000 kilograms per cubic meter at 4 degrees Celsius, 830 times denser than air. Aluminum, 2,700 kilograms per cubic meter, making up 8.23% of Earth's crust. Lead, 11,340 kilograms per cubic meter, an ancient metal used since 9,000 years before the Common Era. Earth's core, 12,600 to 13,000 kilograms per cubic meter, mostly iron-nickel under enormous pressure. Mercury, 13,543 kilograms per cubic meter, the only metal liquid at room temperature. Hassium, 40,700 kilograms per cubic meter, radioactive with a short half-life. The Sun's core, 150,000 kilograms per cubic meter, plasma at 15 million degrees. White dwarfs, 10 billion kilograms per cubic meter, a teaspoon of material weighs several tons, with electron degeneracy pressure preventing collapse. Neutron stars, 10 to the power of 17 kilograms per cubic meter, a 12-kilometer diameter object twice the Sun's mass, with surface gravity 200 billion times Earth's. Hypothetical quark stars, 10 to the power of 23 kilograms per cubic meter, a tennis ball-sized piece weighs as much as Earth. Black holes, theoretical infinite density at the singularity, but in practice bounded by the event horizon. Planck density, 10 to the power of 96 kilograms per cubic meter, equivalent to 10 to the power of 23 suns compressed into 2 atomic particles. Next, photons, particles of light traveling 300,000 kilometers per second without acceleration. From birth, they reach maximum speed, massless, with time standing still for them. In media, speed changes instantly due to interactions, not gradually. Ice ages. Earth has undergone at least 5 global glaciations, starting 2.4 billion years ago, caused by silicate weathering, cyanobacteria, and volcanic CO2 releases to end them. Currently, we may be in an interglacial period, but human-induced global warming is delaying the next ice age. The 1977 discovery of life at Galapagos deep-sea vents, organisms around hydrothermal vents opened possibilities for extraterrestrial life, thriving in extreme heat and pressure without sunlight, relying on chemosynthesis. Fermi paradox. With billions of planets, why the silence? Perhaps a cosmic zoo hypothesis, or we are alone. By 2025, over 5,000 exoplanets confirmed, but no contact. To expand further on black holes, recent advancements in gravitational wave astronomy have revolutionized our understanding. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, along with Virgo and Kagra, not only detects mergers but also provides insights into black hole populations. For instance, the first detected merger in 2015 involved 2 black holes of 36 and 29 solar masses, forming a 62 solar mass black hole, with 3 solar masses converted to energy as gravitational waves. This event, GW 150914, confirmed Einstein's general relativity in strong field regimes and opened a new window to the universe. Since then, catalogues have grown, revealing a continuum of black hole masses and challenging formation models. Some mergers involve black holes in the upper mass gap, between 130 and 200 solar masses, possibly from hierarchical mergers in dense clusters. The Event Horizon Telescope Collaboration's 2019 image of M87's black hole, a 6.5 billion solar mass behemoth, showed a shadowy ring 50 billion kilometers across, matching predictions from general relativity. Follow-up observations in 2022 imaged Sagittarius A star, our galactic center's 4 million solar mass black hole, despite challenges from rapid orbital motion of accreting gas. These images validate the Kerr metric for rotating black holes, where spin drags spacetime, creating ergospheres for energy extraction via the Penrose process. On formation, direct collapse black holes offer a pathway for early supermassive ones. In the young universe, Massive gas clouds collapsed without fragmenting into stars, forming 10,000 to 100,000 solar mass seeds, then growing via accretion and mergers. Simulations suggest population 3 stars, the first generation, metal-free and massive, could produce intermediate seeds. Dark matter halos facilitated rapid growth in overdense regions. Black holes influence galaxy evolution. Active galactic nuclei, powered by supermassive black holes, emit jets regulating star formation via feedback, preventing overgrowth. In the Milky Way, Sagittarius A star's past activity, evidenced by Fermi bubbles, shaped our galaxy. Evaporation via Hawking radiation, though negligible for astrophysical black holes, implies micro-black holes explode if small enough. For a 1 billion-ton primordial black hole, lifetime matches the universe's age, potentially detectable via gamma-ray bursts. Density extremes extend to exotic matter. Beyond neutron stars, strange stars of quark-gluon plasma might exist. Preon stars, hypothetical, denser still. But black holes' event horizons hide singularities where physics breaks down, motivating quantum gravity theories like string theory or loop quantum gravity, predicting finite density cores. Photons' constant speed underpins relativity. In vacuum, exactly 299,792,458 meters per second. Refraction in materials slows effective speed, enabling technologies like fiber optics. Ice age cycles, driven by Milankovitch parameters, orbital variations, occur every 100,000 years. The last glacial maximum 20,000 years ago saw ice sheets covering North America and Europe. Current anthropogenic forcing overrides natural cooling. Hydrothermal vent ecosystems, discovered by the Alvin submersible, host tube worms, clams, and microbes in 300 degrees Celsius waters, sulfur-based. Analogous to potential Enceladus or Europa subsurface. The Fermi paradox solutions proliferate: great filters, self-destruction, or transcendence to higher dimensions. SETI searches, now with machine learning analyzing radio data, yield no signals. Breakthrough LISTEN scans millions of stars. Exoplanet atmospheres via James Webb reveal biosignatures like dimethyl sulfide on K218b, though controversial. In summary, black holes embody cosmic extremes, from formation enigmas to density ultimates, intertwining with life's cosmic context, urging continued exploration.